Welcome to Study Loop.
This is the problem number 2. Here, the problem states that so that energy E must exceed the minimum value of the Vx for every normalizable solution to the time independent Schrodinger equation. And what is the classical analog to this statement? And here there is a hint which is given: rewrite equation 2.5 in the form of the d2 psi by dx square is equal to 2m by h bar square vx minus e and psi. And if e is less than v minimum, then psi and its second derivative always have the same sign, and the argue is that such a function cannot be normalized. Let's do the solution for this question. So this is the problem number 2, and we know the Schrodinger wave equation, that is I h bar del psi by del t is equal to minus h bar square by 2m and del 2 psi by del x square plus vxt and psi xt. This equation can be solved by using the method of the separation of the variables and method of separation of variables by assuming that psi, that is complete wave function psi xt, is equal to there is a function psi x is the function of the x only, and there is another function ft of the this function f is the function of the t only. When we substitute this value in this equation and then get two ordinary equation, which is 1 upon, that is ih bar 1 by ft and del f by del t is equal to e, and second equation is in x only, that is minus h bar square by 2m 1 of on psi x and del 2 psi by del x square is equal to e. So here this uh, first equation is the partial differential equation in the time only, and this is only x only. And the solution of this first equation will be, that is ft is equal to a some normalization constant e power minus I e t by h bar. Hence the complete solution can be written as, that is psi xt is equal to psi of x and a e power minus I e t by h bar. And here a is the normalization constant. And the second equation in this equation 3 is known as the time independent Schrodinger equation, which is, that means this equation is known as the time independent Schrodinger equation. Let's rewrite this equation, which is given in the question, that is as a hint, that is d2 psi equation 3 second. And when this is second equation, this is first equation. This 3 second can be written as d2 psi by dx square is equal to 2m by h bar square, and here v potential energy is the function of the position only, minus E and psi, and here the psi is the function of the x only. Now if E is, which is given in the question, if E is less than V minimum, then this d2 psi by dx square will be positive, and this psi will also be positive. That is, the coefficient of this wave function psi and the will be positive. So in this case, this whole factor will be positive. So hence the second derivative and this wave function will be positive. That means d2 psi by dx square and psi have the same sign, that is positive. If psi is positive, then the d2 psi by dx square will be positive. So here, case number 1, if psi is positive or negative, then second derivative, that is d2 psi by dx square will be positive or negative. It means that if the psi is positive, then the second derivative will be positive. If the psi is negative, then the second derivative will be negative. It means the wave function always come from the axis. Let's find out the normalization condition for this. Assume the wave function is normalizable. Assuming the wave function is normalizable. Let's check the wave function can be normalized or not. We have the normalization condition 1 is equal to minus infinity to plus infinity psi xt and psi xt and dx. So here minus infinity to plus infinity, this value will be a star, or let's write psi of x here, complex conjugate a star and e power plus I e t by h bar into psi of x e power I e t by h bar and h here and dx, and from here you can see that this portion is cancelled. Now here you will get this a star a, and if a is real then it will be, or that is a complex conjugate a will be modulus square and minus, that is psi of x and dx square. That means this wave function is the function of the x only. So here there are some condition, then it may increase or decrease with the value of the x from 0 to minus infinity to plus infinity. So let's discuss these cases here. And if you plot this wave function with the position of x and psi, and this is x. So if psi is positive, then the second derivative will be positive, and if the psi is negative, then the second derivative will also be negative. So here you can notice that if wave function is that is x is increasing, that means the wave function is increasing, and the shape of the curve, that it is a curve wave function. So here we can draw this. It will be like this, and if the psi is negative, then will be. So if the psi is negative, then the second derivative will be negative. If the psi is positive, then second derivative will be positive. And if x is increasing, then the psi will also increase as x is increase. And it is increasing in the positive, that is x is equal to plus infinite, and in this direction it is increasing. Here x is equal to minus infinite, this side, so this is minus x, and similarly here it is increasing in this direction and in the direction. That means such wave function cannot be normalized, because when you increase the value of the x, the wave function is increasing and increasing and becomes bigger and bigger. That means it's never cannot turn toward the x-axis. So it always increasing on this side. So it shows that the wave function is infinite at x is equal to infinite, so which is the contradiction of the Schrodinger wave equation. That means the wave function must be zero at uh, uh, limit x tends to plus minus infinite, psi x must be 0. But in this case, this condition is not satisfied. So if this condition is satisfied, then the wave function can be normalized. But for the given case, the this wave function is increasing as you increase the value of the x to infinite, then psi is increasing, hence the wave function cannot be normalized. So the conclusion is that psi of x cannot be normalized. And this is the general case. That means such wave function which is increasing with the value of the x cannot be normalized, for which the second derivative is positive. If the psi is positive, if the psi is negative, then the second derivative of will also be negative. So such wave function cannot be normalized.